Okay, so as you know, the exam is on Wednesday. For the exam, like I had sent like an announcement like with a recommendation, like you should like now that we have covered all the material, like yeah, start by checking the practice exams. Then the workshops are all practice exam problems, so they're kind of more or less exchange interchangeable with the old exams. And then after you do the workshops and the practice exams, like you can check the like the quiz problems and the true false grade code problem assignment and the examples that we have done in class. And after that, you should do MyLab, as a like in terms of priority. So if you have to like if you're running like if you don't have enough like a lot of time and you have to choose between like going through all the exam problems or like finishing some MyLab assignments, I would say go through the old exams. So in practice, many of the MyLab questions sometimes, especially at the beginning of the course, like later, there's like a less of like a difference. But sometimes like the MyLab questions, like they're more like meant to getting you acquainted with computing things like in a more efficient way and things like that. But if you want to have like a better like sense of like what to expect, it's just prefer to just look at the exam, the old exams that I have posted on Canvas. The exam will be kind of like still six problems, and essentially the format is like the one of the old exams. So start there, and on Wednesday I managed to get like a room for the office hours. So I just sent you an announcement about that. The room is here in Beck Hall. So I'll have the office hours there because like my office in Hill Center is kind of too small. So if you want to come earlier and stay there, like ask questions, and you can do so. And then Karuna, the TA, will also give you extra office hours tomorrow because that's the other thing I wanted to say. So remember, like usually we have the recitation on Thursdays, right? But so it doesn't make sense to have the recitation the day after the exam. So like there's no recitation this week. Instead, like you have like extra office hours that Karuna is giving, tomorrow and I think today as well, if I'm not mistaken. So that's why I didn't send you like an announcement with what to study for the quiz because there's no recitation on Thursday. Is that making sense? So if you go over the practice exams and the workshop problems, yes, the overwhelming majority of the exams should just like look familiar to that. So like will be well prepared for that. And then you can like finish covering the details, like, going over like, the grade scope assignment. I changed the deadline for the algebra assignment until the end of the week if you haven't finished it. It's very quick, but again, like you may want like this 30 minutes, extra 30 minutes to do some other problems. So and yeah, like, and again, obviously, like if you can do my lab, do as much as you can, but it's not, don't start there, like just like finish there, depending on how much time you have left. Okay. Cool, but yeah, like the exam is like, again, like the types of problems you'll see, they are really very similar to the stuff we have been doing. So I don't think there you'll see like any like big surprises or anything like that. So for today, we had to talk about partial derivatives, which is that is actually like one of the first big, really important topic of multivariable calculus. Because until now, we really haven't done too much with calculus, if you think about it. But now we're going to discuss how to take derivatives, which is like a more traditional calculus topic. So to set the stage, let's just think about f of x, y as a function of two variables. Okay, and there are a couple of ways to think about this function. Um, So there are a few ways you can think about this function. The I think the best way to think about this is that if you have like a point x, y on the plane, and let's say you have a point on the plane, and think of this like as an, here's like an analogy. So like, or like more like a possible interpretation of that. What's my eraser? Oh, here you are. So like, it's useful to think of f as like a quantity that depends on the point on the plane that you are sitting on. So for example, like it could be temperature, like that's kind of like my very favorite interpretation for these type of things. So f could be the temperature at the point x comma y. So for example, maybe here, like, let's say this is like the point four comma, maybe this is like the point 4,1. Right? So if I write f of 4,1 equals 50, like, you could think of that as being like, oh, the temperature at this point is 50 degrees, right? That's like a way to think about it. And if then there's like another point, like what could this point be? Like maybe this is -3,4, I don't know. And if I write f of -3,4 equals negative, like, well, let's put like a different value for temperature, like 20, then you would say, oh, the temperature at this particular point is like 20 Fahrenheit or 20 Celsius, like whatever, like feet you're using. So, one way to think about like a function of two variables that depends on x and y would be of like, to any point on the plane, you kind of like assign a number, which is like the value of that function there. So it could be the temperature. If you think about, it could also be like the atmospheric pressure at that point, right? So atmospheric pressure. If you think of like actually like on a, you have like a mountain or something, like some sort of like terrain, then like, like the value of the function could just tell you the height of the mountain at a given point. So f of x comma y would be the height of the mountain. Right. So depending on like the particular interpretation you're giving to the function, you'll think about in different ways about what it is, but the idea is like, for any point on the plane, you have a number, and again, the number could be the temperature, could be the pressure, could be the height, or something else. So what if you think about this in Calc 1, so what was the derivative in Calc 1? Usually we won't use like the prime notation in this course. For derivatives, it's better to indicate with respect to which variable you're taking the derivative. You'll see that in a moment. But if you remember like what the definition or the derivative was interpreted as in Calc 1, it was like the rate of change of f with respect to x, right? So what that meant is like how much f changes, like how fast f is changing when you change the value of x a little bit, right? So So let me put it like this, change in f divided by the change in x, right? Okay, so now, the, the situation that we have is like, you have this point x comma y, and you want to understand like how the function changes, when you move a little bit, right? So the issue now, or the difference is that now you can move in different ways because now you are on the plane. So for example, if like I'm measuring the temperature at a particular point, right? I could measure like, let's say this is a northwest, southeast, right? So you could ask how much is the temperature changing when you move towards like westward, right? Like in this direction, or like how much is the temperature changing when you're moving south, which would be towards you. So, in this case, like, there are different ways that you can move. So you could move. So like, if you are at this point x comma y, you could move this way, right? So how can we think about that? That's moving parallel to the x-axis. So you could ask like how the function changes. Okay. Or you could also move this way, which is parallel to the y-axis. So you could also ask how the function changes. Okay, so again, like if you think about this like as roads, you like what I'm saying is that you could imagine like the temperature changing at a different rate when you drive along the yellow road versus like the pink road, right? Like that kind of is reasonable. So depending on which of these two roads you choose, right? Like there is like a corresponding derivative that you can take, and that gives you like the rate of change in that direction. That makes sense. So that's where like the idea of the partial derivative will kick in, because the idea is like before, when like the function only depends on x, when the function only depends on one variable, there's only one way to move along that variable. Like, you can either increase x or increase or decrease x. But when the function depends on x and y, you can either increase x, decrease x, or increase y and or decrease y, right? So you have like two possibilities on what you want to change. So for each option, like you get like a corresponding derivative. So let's think about. Let's think about what this should be. So if you're moving parallel to the x-axis, right? What happened there? So if you move parallel to the x-axis, you can say this like this line kind of passes through a given value for y. So in other words, what happens here when you move along the yellow line is that x is changing, right? But the value for y is fixed. Is that okay? So in this case, what we're varying is the x. So the derivative that we're going to take is with respect to x. So that's how we're going to think about it in this context. So let me write that down like this. So this is called the partial derivative of f with respect to x. So this is a partial derivative. And why is that? So that is the rate of change of f with respect to x pretending or considering the y variable actually as a constant. So if you think about it again, in this case, like of the line, when you move along this line, you have fixed secretly the value for y. The only value for x, the only variable that's changing is actually the x variable. So the idea of like a partial derivative is kind of like to take a derivative one at a time where you only work with a variable and pretend that the other variable is kind of like a constant for the time being. So by pretending, by treating y as a variable, as a constant, y as fixed. So in terms of notation, like the notation that you use for the derivatives, it's kind of like the usual derivative notation, but if you think about it, you just make like the d a little bit more curly, just to emphasize that there are more like derivatives or more variables around. So when you write something like df dx in the usual Calc 1 sense, you're thinking of f as just like a function of one variable. So that's why you kind of like write it this way. But if you write it this way, you want to distinguish this situation from this situation because you want to say, oh, there are other variables around. It's just that we're not considering them at the time being. So that's why you change the notation a little bit to like remind you that this function depends not only on x, but also on y, and later on z when we deal with functions of three variables. The good thing is that essentially the way to take derivatives is like a nice thing about many of the things in this course. The way to take derivatives is exactly the same way you take derivatives in Calc 1. You just have to act as if one of the variables is like a constant. So before like, keep writing more stuff, let me give you a quick example of what I mean. So if you take so let's say you have like a very simple function of two variables, like which is just x squared times y cubed. So if I ask you to find the partial derivative of f with respect to x, what does that mean? So I'm going to find the partial derivative with respect to x of x squared y cubed, right? So what this notation means is that take like the ordinary derivative of Calc 1 with respect to x by pretending that y is a constant. So here just pretend that y is a constant. Okay, so so really you, in your mind, you have to think that y cubed is kind of like pi cubed or like e cubed or 2 cubed, like, like just like a number cubed. So if you remember, like when you have like a number, like you can take it out of a derivative, right? So you can take this y cubed outside the derivative because now it's like a constant. And now you are just taking the derivative of x squared with respect to x, and that is really the same as before. So that's just 2x. So it is like agrees with the ordinary Calc 1 derivative. So it's just 2x. I mean, you get 2x, and because of the y cube, you get 2x y cube. Okay, so that is what the derivative with respect to x would be. Is that making sense? Oh, I got it. So really, like to find the derivative is just like the same as before. It can be mentally a bit more tricky because you do have to remember that you're pretending that one of the variables is constant. But except for that, there is everything else is computed in exactly the same way as previously. Okay. So like, what would that tell you? This is how, like, again, if you think about this in terms of temperature, this would be like, how fast is the temperature changing when you move parallel to the x-axis? Okay, questions up to this point? Yeah.
So if you're doing like x squared plus y cubed with the y cubed is going.
Yeah, perfect. Let's think about that one. Yes. Good. Yeah, so if you or to put here like x squared plus y cubed, right? The derivative of a sum is the sum of derivatives, right? So this is like the derivative with respect to x of x squared plus the derivative with respect to x of y cubed, right? Good. And then the first factor, right, is just 2x because of what we were saying. And now this is really like pretending that y is a constant. It's like 2 cubed. It's kind of like a number, right? So like the derivative of a constant or a number is just 0. So you get 2x plus 0, so you get 2x. Good. Is that making sense? Um, so it really does work as, the usual way in which derivatives tend to work with this additional thing that you have to do which is remember that, you know, you're treating one of the variables as a constant. And then there's exactly a same a parallel story that's happening for the other variable because again, if you're located here, you could have chosen to move parallel to the y-axis, right? If you choose to move parallel to the y-axis, well, you can see that like the y values can change along this road or this line. The only thing that you're fixing is x, right? So secretly, if you move parallel to the y-axis, you're treating x as a constant. So there's like an analogous derivative, which I'm about to write, which is called the partial derivative of f with respect to y, where you do exactly the same thing, but with the roles reversed. So let's write that down here. With respect to y. And so this is the rate of change of f with respect to y by treating x as a constant. While treating x as a constant. And yeah, let's just take the same function as before. I'll do it in both cases because there's not too much of a difference here. So now the idea is that because it is a derivative with respect to y, x is like a constant, so you can take x squared out of the derivative. And the derivative of y cubed with respect to y is like, the same as in Calc 1. It's just 3y squared. Okay, so you get y squared. And like if you had a sum, like something similar happens here, but now it is the first term that vanishes. So this one gives you 0 now. The difference is this one gives you 0, and the other one gives you just 3y squared. So you just get 3y squared in this case. Is that okay? Is that making sense? So far, so good. Okay, so what comes next So this is in general like how you would take derivatives in this context. There is something new that happens. So if you think about it, in Calc 1, again, like, like, yeah, if you have like a function, you could theoretically take the second, I mean, if the function is nice enough, you could take the first, second, third, fourth, fifth, sixth derivatives, blah, 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 blah. In practice, like only the first two really matter, like if you think about it, like you only really use the first and second derivative to extract useful information about the function, at least like for the applications that you have in mind in Calc 1. So like, the first derivative typically was to, like, if you think about this in max-min problems, right? The first derivative was to find the critical points of the function. Maybe you remember that's where the derivative became 0. And then you would like to classify the critical points as a max or a min. And there were two ways to do that, but like one way is like to use the second derivative test, right? So you would look like at the concavity. So there's going to be like an analogous story that happens in this context, which we'll talk about like maybe in 2 or 3 classes, where we will also like try to find like critical points of a function. So that would be kind of like that, like if you think about the function as temperature, that would be kind of like, where's the hottest point on the room, or the coldest point on the room? That would be the max or the mean for the temperature. So there's kind of like an analog of a critical point here that I'll give you the definition again, like in a few classes. And then you would also like to classify them. And for classification of them, like you do require like a version of the second derivative test. So in this class, it's also useful to think about what the second derivative of a function is. And here things do get a little bit more interesting. So let me do like a diagram to explain what's going on. Because something new happens that didn't occur before. So this now what I want to talk about is second derivatives. So if you have like this function we have been working with, what I was saying is that you can take let's draw this more like in as a diagram. You could take a derivative with respect to x, and for that I use the yellow color, right? So that's what we found. So taking like the yellow road is kind of like taking the derivative with respect to x. When taking the pink road or the red road is like the derivative with respect to y. Okay. So taking like, if you think about the function as being at the top level, like taking the derivative lowers, you go down one level. And then, so this is where the first derivatives live. And then the second derivatives live one level below, right? If you think about this in a diagram. So the question is like, how can you get down from now this level to this level? So another way, like one way to get down is kind of like to do kind of like the pure cases. By that I mean yellow, yellow, or pink, pink. Okay. So if you're here, right, you can go down another level by taking a second derivative with respect to x. So I'll write that down in a moment. So I'm just saying like that we're going to take a derivative with respect to x of this thing. And again, now the 2y cubed is just to show you all the steps. The 2y cubed is now like the constant. So you're taking the derivative with respect to x of x. And the derivative of x with respect to x is just 1, right? If you remember that. So this is 2y cubed, right? So how did we obtain this from the top level? We kind of went down twice. So what you would like to say is that the second derivative of this function with respect to x is 2y cubed. So let me write that down in terms of the notation. And I mean, hopefully this looks like a reasonable notation, because if you remember, what's the notation for like in Calc 1 for the second derivative? You know, you would have had something like this. It looks exactly the same because like literally you are supposed to pretend when I take the partial derivative with respect to x twice, I'm pretending that y was a constant twice. So it really does behave like y cubed does behave like pi cubed. That's why I'm putting like a pi here to emphasize that is essentially the same form, like the same result, except that here there's like now it's like there's like a y in our context. Okay, is that making sense? Like how I'm writing this down? So that's what we like the second derivative with respect to x. And then, you know, so here, like, this is like kind of like the function, this level is where the first derivatives live. And this is one of the, what you would like to think of as the second derivatives, right? So that's one option. But there's another option that's kind of obvious, which is like, oh, you could have gone with the pink road twice, right? So you started, you also were at this level, and then to go one level down, you can use like this road again, right? Like this derivative with respect to y. So okay, hopefully now you see how this is supposed to work, right? So you take the 3x squared out because it's like a constant. So you're just taking the derivative of y squared, which is 2y. So you multiply 3x squared by 2y, so you get 6x squared y. And that would be the second derivative of the, if you think about it, like in terms of the original thing you started with, you went down once with y and another time down with y. So this is like the second derivative of the function with respect to y. So you would like to write this as the second derivative with respect to y of x squared y cubed equals 6x squared y. Is that making sense? So far so good. And let me try to draw like a line to distinguish like the different levels. Here's level. So this is like the function level, the level of first derivatives, and here I'm putting like the stuff that has to do with second derivatives, right? The question is that you can ask now whether this is already all that you could have like compute, right? So actually there's some stuff that I haven't drawn yet, right? Like there's some, you know, there is a few other ways to get from, you know, from this level to this level. I don't know if anyone can think about it. Yeah,
You can take the partial derivative with respect to y, or the partial derivative with respect to x.
right. So you can kind of like combine the roads if you want to think about it that way. So here, like you go down with x, but then you could also go down with y, for example, right? So do like x, y, or y, x. So for example, I know another way to lower a level here is that take this, but go down with respect using y. Right? And what do you get here? You get 2x is like a constant now. So you're just taking the derivative of y cubed. And if you remember, the derivative of y cubed is 3y squared, right? So you get, well, let me put it like this. Okay, so that is what we get if we do x and then y. So one way to write this, Let me. One way to write this is that you're saying like, you did the derivative first with respect to x. You did the derivative first with respect to x. Out of what, of the thing that you get, you do the derivative then with respect to y. So I'm saying that that's 6xy squared. Okay, so that would be the derivative. And then, so like here it's like doing yellow, then pink, right? The other thing I could do is like pink, then yellow, right? If you think about it. So what would that be? That would be taking the derivative with respect to x of this thing. Right? And what do you get here? Well, now y squared is like the constant, so you're just thinking derivative of x squared with respect to x, which is 2x. And so you get what? You get 6xy squared. So what is that? So what do you would like to say in this case? Is that you did first the derivative with respect to y of x squared y cubed. And then that with respect to x, and then you're finding 6xy squared. To if like if you notice of the things that I'm putting in boxes, right? Like so this is x derivative of x, right? This is the derivative of y, and then this is x, then y, and then y, then x, right? So like you can kind of see there, like there is an agreement between, like in general, like like the derivatives can be completely different from one another, right? Like these, like is not the same, and this is not the same as this one. But actually, what does happen in general is that these do agree. So the mixed root or the mixed term or the mixed partial derivative, which is how it's called, they do give you the same answer. So let's just think about that for a second, what it means. What this is saying is that if you think about it in terms of the temperature, this could mean, for example, how much is the temperature changing when you're moving in the north-south direction and then in the east-west? And what that is saying is that this is the same as moving first in the east-west direction and then in the north-south direction. So when you move in along perpendicular directions, the rates of change do not, doesn't matter which one you find first, like they do give you the same result. So let me write that down. So what I'm trying to say is that you have, so how many secondary partial derivatives you have? You have this one, which means take the derivative of f with respect to x twice. So that is just x. Then the other one is y. So this is. And then you have the mixed terms, right, which I'll write this way. So what this means is I take the derivative once with respect to y and then x, or once with respect to x and then y. So it doesn't matter in which order you do it. So take derivative with respect to x once. With respect to x once and then y. Or take derivative um, with respect to y once and then x. So but they give the same result. Does that make sense?
One, yeah, let me see.
So, right, the thing is like, okay, the first one is XX, right? Let's, okay, so it's better to think about it in colors. Like one is yellow, yellow, right? The other is pink, pink, the other is yellow, pink, right? So what I'm saying is that when it's like yellow, yellow or pink, pink, right? Or yellow, pink, there are like different combinations, right? Like, so that's why you wouldn't expect those to agree at all with one another because you are different, doing different procedures, right? But so that's why, like, for example, this one disagrees from this one. But when you do something like the ones in the middle, right? The ones in the middle are kind of like doing pink, yellow, or yellow, pink. So that, like, what I'm saying is that in that case, they are like what matters what this is telling you is like what matters at the end of the day is like, how many times you apply the color, not in which order you apply them, right? So it matters if it's twice yellow or twice pink or once yellow, once pink, but not whether pink comes before yellow or vice versa. So that is kind of like the point of doing this, because if you think about it, like, you know, again, like these mixed derivatives, like what they're telling you is like, how much is the temperature changing when you move first with respect to x and then move with respect to y. But the thing is like, what happens is like the x and the y directions are perpendicular to one another. So knowing, they kind of do not, like moving in one direction does not interfere with what happens when you move in the other direction. So that's why the rates of change are kind of like blind to which one you did first. But in the other ones, if you kind of like change with respect to x twice, then yeah, that is different from just doing like x and then y or something like that. Is that making sense? Let me do another example with another function so that we see this a little bit better. So actually, this is a nice one because it's also like it's more like related to the chain rule. So I will go to this side, which is a bit of a mess. And there, so I don't know if there's any other questions before I erase this. Um, okay, so let's say the function had been x squared sine y. So what I'm saying is that there are two ways to get to the second derivative. So you can do the derivative with respect to x, right? So when you do the first derivative with respect to x, okay, sine of y is like a constant, so you just get 2x sine of y. Okay, so this is like the first derivative. You can still go down another level by like taking another derivative with respect to x. In fact, like, let me not write all these like partials with respect to x because I think this just makes the diagrams too big, too messy. So I'm taking another derivative here. And again, sine of y is like a constant, so it's like kind of like a taking the derivative of x with respect to x. So that's what you get by going down with twice with respect to x. So that's why I would like to say that the second derivative with respect to x of this function is 2 sine of y. That making sense? And then you can do the same for y twice. So if you do the same for y twice, again, sorry, I should want to avoid trying to draw this. Okay, the derivative of a sine is like cosine, so you get here x squared cosine of y, right? And then you do another derivative with respect to y. And this just gives you minus x squared sine of y. Okay, so since that is what you get after going down with y twice, that's, you would like to say that the second derivative with respect to y, this thing minus x squared sine of y. Okay. And then what you can do is like the hybrid ones. So again, this is yellow, yellow, pink, pink, and you see like they're completely different from one another, right? Like if you compare them, like like it's not that it is impossible for them to agree. It's just that in general, you wouldn't expect them to agree. So the bet that you should make is that in general, they're very different. Okay. But then, again, what you could do is kind of like, combine the paths, so like, or the, like the roads. So like you go yellow and then pink. And you find, what is this? 2x cosine of y. Or, you do pink and then yellow, so you can. And that had actually, like, again, the point is that it gives you 2x cosine of y. Again, so this is 2x cosine of y. So they do agree, like these two agree. So what you would like to say is that, if you think about it, what this is saying is that taking the derivative first with respect to x and then y is the same as taking it first with respect to y and then x. So when it comes to the mixed ones, the order does not matter. So it does take a little bit of time to get used to it, but the point of like of this is that it is like, when you look at this, like you could have thought, oh, what should I do first? Like y or x? And what I'm trying to say is that it doesn't matter which one you do first. Like you could have done y and then x or x and then y. And you still get the same result. Uh, Okay, so that is the first thing that I have to tell you about today, which is like how to find these partial derivatives. Um, how to compute them. So in practice, like you compute them like just like using the same rules for derivatives from top one, like that, like nothing really changes because it is like taking like ordinary derivatives, but again, just like by treating one of the variables as a constant. The other thing that's common in Calc 1 is like these chain rule problems. But so let's just talk about the chain rule. So just to start with the Calc 1 chain rule, because should serve as a reminder. Let's say that you have like a function of x, like for example, e to the x. So you have e to the x, and then you make a change of variables like like x equals t squared. Right, so what that means like is that you can think of f as a function of t. So you would write something like f of t equals e to the t squared, right? And so like the chain rule, like, and this was kind of like the most complicated rule for derivatives in Calc 1, like the chain rule would give you like the formula for finding the derivative of e to the t squared, right? Which you have done already multiple times, so you probably don't even think about it, but oh, it's times 2t, right? So in this case, the derivative of e to the t squared is just 2t e to the t squared. Right? The way you would do this, like the first few times, like you would memorize this, is that you would write something like, well, what's the derivative? And this was the chain rule, right? Like you would say, what's the derivative of f with respect to t? And this is where like this notation is kind of like superior because it allows you to do things like this and you still get the right answer. So you kind of would multiply and divide by the x, right? And so you would say, oh, okay, this is the f dx. It's like the derivative of the exponential, which is e to the x, and the x dt is just 2t, right? So you get 2t e to the x, and this is essentially the same answer if you just remember that x equals t squared, right? So you would get like like the chain rule. Like the point of the chain rule is kind of to say how much f varies with respect to t is how much f varies with respect to x times the variation of x with respect to t, right? Which in terms like working with fractions, which they're not really fractions, but if you write them as fractions, it just looks like you're doing nothing very useful, right? Because they cancel out. So that's kind of like the nice thing of presenting it this way. What's somewhat more useful, which I don't know if you saw it that way, but this is like a useful way to draw the chain rule as a diagram. Is that you have the function which is e to the x, right? And below it, I'm going to put the variable on which it depends. Okay, so e to the x is a function of x. But x now is a function of t, right? So I'm going to put a level below x, the t, because that is what x depends on. So you start kind of like with a diagram where you have function, the variable on which the function depends, and then new variable on which everything is going to depend on. So one way to think about this chain rule is that you want to find, again, similar to this thing, you want kind of going down is taking like a derivative. So you want to find the derivative of, let's write here the function f. So you want to find the derivative of the function with respect to t, right? And then what the chain rule says is like, well, instead of finding this rate of change directly, you can kind of like find how much you know, each like of these sub levels depend on with respect to one another. So like, instead of going from, I don't know, think of this as top level to bottom level, you can go first through the middle. So that's df dx. And then go from the middle to the bottom, which is dx dt. And so what the chain rule says is that if you break the total path into pieces, the total change is just the product of the meaning changes or the individual changes. So df dx, df dt becomes df dx, dx dt. That makes sense, of course, like how this works. Okay, so my point is that there is a version of the chain rule, which is exactly more or less the same idea, but with more variables involved. So let me just like do a concrete example, then I'll show you how this looks like from a diagrammatic perspective, because it's kind of useful to draw it like using diagrams here. So let's say here's like our case. So what could happen in our situation is like maybe you have like a function of two variables, like x times y, right? And then you are told, well, maybe x and y depend on two variables. So let's just say that x is t plus s, and then y is so what that means is like, if you're giving x and y in terms of new variables, when does that happen? That happens, for example, in polar coordinates, right? So if you think about it in terms of polar, just to make a remark here. If you write something like in polar, like then you're thinking of x and y in terms of new variables, right? So we're kind of doing like an analog of that, where you're thinking of x and y in terms of new variables. And it's not like a completely crazy thing, because again, you do that in polar coordinates. That's the point of polar coordinates. So you can think of like, a point, instead of being described with x with Cartesian coordinates, it could be described in terms of other variables. Okay, and this we'll use a lot of the time later on. But for now, like, you just think about this like in a very simple way. Then you would say, that like the function really like, if you make the direct substitution, then you can think of the function as depending on T and S. Which, what would that be? It is what you get by just doing a direct plug in. So you would, X is T plus, becomes T plus S, and Y becomes T squared S. Right? And I mean, if you want to, like, you can multiply them to write it in a different way, so this gives you T cube S, right, if you did this one, plus T squared S squared. Okay? So that's what you would get, after doing the substitution. Okay, and now in terms of the new variables, you could find the partial derivatives, which is kind of similar to what we did here. Like here we had like a new variable, which was t, and we find the derivative in terms of t. And like, in this particular case, you can find the derivative of f with respect to t just by doing like the actual, partial derivatives. So what is the derivative in this case? You get 3t squared s plus 2t s squared, and what would be the derivative with respect to s? Which would be t cubed plus 2s 2t squared s. That makes sense. So that is like, what you would get if you were to substitute everything like directly into the formula, right? And then, just taking the partial derivatives the way I was telling you to take them, right? So that is like the derivative you just obtained by direct substitution. Now, what the chain rule says, what was the chain rule in Calc 1? It was like, how do you relate the derivative with respect to the new variable in terms of the derivative with respect to the old variable? So there's like a similar situation that happens here, where you can find these partial derivatives with respect to the new variables in terms of the partial derivatives with respect to the old variables. So what the chain rule does is how to find the partial derivatives of the new variables with respect to the new variables in terms with respect to the old ones. So let me kind of show you uh, like how that works in terms of the diagrams before writing the chain rule. So the idea is, this is sometimes called like tree diagrams or chain rule diagrams. But the idea is like, if you have like the function, right? Think of, you have like the function f, which depends like originally on x and y. So let's put x and y here, right? But then x and y depend on t and s. So let's put here t and s. So you're thinking like, you know, you start with the function, the level below you put the variables on which the function originally depends, and the level below you put the variables on which each variable depends. In this case, like you could also like kind of like draw it where like T and S are kind of, you know, like just written once on the diagram, but you know, I think it's easier to do it this way because it puts more emphasis on what's about to happen. So for example, if you wanted to find the yeah, like actually let me, I think it would look better in terms of the diagram if I write it like this. So I'm just saying that X depends on TNS and Y depends on TNS. So that's another way to put them, but it looks less confusing when with the stuff that I'm about to do next. So you kind of connect the, you know, you connect with segments or curves, like the different variables depending on how they depend on one another. So what the chain rule says is like, imagine that you wanted the derivative of f with respect to t, right? So you want to know how much f depends on t. So if you think about it kind of like as in terms of the diagram where you're thinking of like before, you had like the function f, x, and t, and there was kind of like, you know, what we did is kind of break the bigger path into two pieces, right? So for example, what is one piece that you see here? You would see this piece, you would see this, you could go from f to t by going from f to x, and then from x to t. Okay, so that one, let me put arrows to indicate like the direction. Okay, so when you go from f to x, like every time you go down, you take a derivative. So when you go from f to x, you take the derivative of f with respect to x. And when you go from x to t, you take the derivative with respect to t. Okay. So this particular path gives you like a contribution to this rate of change, which is just like what you get by multiplying these two together, because that's essentially what would have happened before, right? So before in cup one, this was exactly the chain rule if you just put like these like in the usual, like with the usual notation, like straighten them out. Okay. So that is what you would have had before. Okay. The difference now is what happens that that's not the only way to get to T if you think about it. There's another route that you can take to get to T. So what's another way you can go to T? You could start with Y, right? You could go from F to Y and then from Y to T. So this is like another particular trajectory, so or path. So when going from F to Y, you take the derivative of F with respect to Y, and then from Y to T, you take the derivative of Y to T. So again, like you should think of each of these kind of like as individual chain rules, right? For each of the variables, and then you just the point of the chain rule is to add together the contributions because they're kind of like a non like independent paths. So like you know what you should get in this situation is just what you get in this situation is like the contribution coming from the green path plus the contribution coming from the white path. And similarly, if I'll show you this in an example how it looks like with what we were just doing, but I want to write this down before we finish. So similarly, if you wanted to find say like the derivative with respect to s, I'll draw these diagrams in a less confusing, without drawing all of this so that it's less confusing. So if you wanted to find the derivative of f with respect to s, what you have to ask is how many ways do I have to go from going from f to s? So what is a potential way? You could go from you could go from F to X and then from X to S. So that's one path. So every time you go down, you take a derivative. And you multiply the contribution. Or, let me see which color I haven't used. I haven't used the pink one. Or you could go, what's the other route that you can take for going from F to S? You could go from F to Y and or Y to S. So when you go from F to Y, you take the derivative of F with respect to Y. And then when you go from Y to S, you take the derivative of Y with respect to S. So if you think about it, each of like the things that I'm putting on with some color is kind of like a chain rule, like an individual chain rule from Cal one. And what the results, like what the chain rule says is that you just add up the mini chain rules like you have here. So that's kind of like the total contribution for let me draw like in the like 5 minutes that we have left. Let me show you how this looks like for this particular function. So I don't want to erase this because like that way we can compare it with what we had. But in our example, what was the function? It was x times y, right? So in our example, the function is x times y, right? And x was t plus s. So x was t plus s, and y was it t squared s? Yes. So you put here x, y. Right, so you put top level the function, middle level the variables on which the function originally depends, and bottom level the new variables. So what this is saying is that if you wanted, what this is saying is that if you want the derivative of f with respect to t, oh, it's just that I wrote. So let's try to work it out. You go from f to x and then from x to t. And then go from f to y and then y to t. So f to y. So what does that give you for this particular example? So this gives you, what is the derivative of f with respect to x? The derivative of f with respect to x is just y. And what's the derivative of x with respect to t? The derivative of x with respect to t is just 1. And then what's the derivative of f with respect to y? That's just x. And what's the derivative of y with respect to t? That's 2ts. So you get that, and we're almost done. The only thing that you have to do left is what is y? Y is t squared s. So you get t squared s plus x, which is t plus s. Okay, so this gives you what? This gives you t squared s plus, you can distribute this, so you get 2t squared s plus 2t s squared. And this 2 gives you 3 t squared s, and then plus 2t s squared, which is exactly the same thing that we had before. Okay, so this way does give you like an alternative route for finding the partial derivatives after the change of variables. So I'll probably do another example about this next Monday after, because like once we have the exam, so I cannot do any more examples. I'll do a more interesting example where you can see like how this gets applied. In fact, we'll see it with directional derivatives, which is will be the next topic. But maybe before we wrap up, is there any questions about this? How this works? So these diagrams like do help you a lot to memorize the chain rules properties. But like essentially, it is actually like some sort of network. If you thought about like you can think about this as a person and then like friends and then friends of friends. So like you're asking like how many ways there are to connect like one person to like a group, another group of people. And in fact, like there is like some matrix multiplication happening here hidden in this stuff. But yeah, like we'll just leave it at the level of diagrams. So again, just read the announcement that I sent you with the information about where the